Good afternoon, everyone. My name is Tu. I'm a final year PhD student from the University of Bath. And today I'm going to tell you about my research, which is about neural rendering and inverse rendering using physical inductive biases. And before I start, I just want to make sure that everyone to know that when I talk about rendering, I'm talking about taking some scene description, which is in this case, some geometry, some texture and some lighting, and produce an image out of it. And as you might have guessed, when I talk about inverse rendering, I'm talking about going from an image and you're trying to recover the input, the underlying geometry and texture that describe that image. Okay, so when we talk about rendering, we think about all of this amazing animation that we've seen on movies nowadays. I'm talking about Pixar movies, I'm talking about visual effects, I'm talking about really high quality architecture visualization. And all of this start from some artist somewhere trying to model all of the geometry, which is in this case all of this mesh, and then apply texture and then render it out to get the final images. And this process involves a lot of work. So you have to first have to model the geometry and then apply the lighting and then render it multiple times. So although we have really, really high quality images that can be produced now from the computer graphics pipeline, they take a lot of work. And more importantly, even when all of this modeling work is done, it still takes a really long time to actually render, to actually produce the images from all of this input. So that's computer graphics. We have really high quality images, but actually takes a lot of work to produce. On the other hand, in the computer vision and machine learning community, especially with the recent generative models, we constantly got bombarded with like really high quality images from all of these GAN models. So this paper, for example, in StyleGAN, they managed to produce images at 1024 by 1024 of like really, really realistic face images. And this caught the internet by storm, right? Everyone's freaking out about how, oh my gosh, like we have all of these fake images that are going to be generated. But actually, if you are an artist and you want to use these models, it's actually non-trivial, because all of this model, what it can do is that it can give you some random sample of the images. So you can get some really nice random faces. But if you're an artist trying to do animation, for example, and you want to say, I want this face at this particular angle or at this particular lighting, it's actually still very hard to do. And in order to do that, you actually need label during training. So for example, in this case, you can see that you can generate the face at a particular angle, but actually during training, you have to provide both the pose information and the image information to the model during training. And you can see how this can be quite limiting when you want to scale this up to other types of data, like indoor data set or even objects, other objects and faces. So you either have uncontrolled random sample generative models, or for conditional image generative models, we need labels during training. And recently there have been efforts in what we call unsupervised disentangled representation learning that tries to tear apart this representation learned by these generative models into independent factors. For example, here, the InfoGAN models managed to learn a factorial representation between pose information and the identity information, so that when you varying the pose variables, only the pose of the chair changes. You can see the chair rotated, but not the identity of the chair. But this works, this kind of unsupervised disentangled representation learning works is still quite early on, so the quality is not great. And they've only worked mostly on synthetic, simple background data. And then you have StyleGAN, which has attracted lots of work in terms of trying to do, trying to take the trend model and trying to do post optimization to tear apart the disentangled representation, and that achieves some sort of success, but the optimization step is also non-trivial. And if you look at these models, these generative models, they, apart from the disentangled representation learning struggle, there's one thing that's really important for this model is that they actually don't understand 3D that well. So here for example, if you look at this row, for example, when you rotate the chairs, you can see that there's a lot of artifacts going on. And the reason is that if you look at the architecture of these models, right, ranging from the DC GAN architecture all the way to the style GAN architecture, they have the same components. They use 2D convolutions. Yes, they stack multiple layers. You use all sort of normalization, all of that jazz on top, but underlie it all, you still have a 2D convolution, 2D kernels. And if you think about it, if you're trying to represent a 3D rotation with a 2D kernel, it's actually a very hard job. And it's actually amazing that these models managed to learn anything 3D at all with these 2D kernels. But as you can see, they still struggle a lot when it comes to rotation, when it comes to relighting or retexture, all of the tasks that actually requires better 3D understanding from this model. So in my work, I investigated in exactly this problem. I look into how we can add the knowledge of the 3D world and how the image that we got is formed from this world, and use that knowledge to this apply these neural networks to improve both the rendering task and the inverse rendering task. And so that's the motivation. And now I'm going to go through 3 of my works that I actually build on top of this idea. The first one is RenderNet, which is basically learning to render. And the next one is Polygon, which is a generative model that learns a 3D representation directly from 2D images. And finally, Blockgan, which is a generative model that learns a scene representation that can be composed to multiple objects. So the first one is RenderNet, and it's starting from an observation that when you want to do inverse rendering, it's very useful to have a differentiable renderer, so you can do optimization. The problem is at the time, differentiable renderers are still at a very early age. So you have OpenVR from the MPI, and then you have all the mesh renderers. The problem is they solve differentiability. You can categorize them into 2 ways. You solve differentiability by either approximate the gradients, which is what's happening here with neural mesh renderer and the differentiable ray tracer, or you try to come up with an approximate but differentiable renderer, which is what's happening here with OpenVR. And the thing is, because here in this work, they basically hand design all of the gradients, they have to make a lot of assumptions. And that means that each of these renderers only work with a particular type renderer. And to apply this to real world data set is actually non-trivial, and some of them actually doesn't deal with occlusion well. So our motivation is that, can we actually learn this renderer? Because we know that from learning depends on data, it can work on any types of data. It can be fast once trained as a feedforward network. So we're just like, okay, can we learn to render instead of having to write down all these gradients? And before we even do that, we actually went back to the computer graphics literature and really asked ourselves what is actually involved in the rendering engine. And for rendering, you can summarize them into 2 steps. The first one is compute visibility. So given the scene and the camera pose, which object is actually being seen from this camera location. And once you know which object is being seen and which object is blocking the other, you compute the shading, which is basically computing the color of each pixel on the render images. So that's rendering in a nutshell. And another thing that another insight that we use when we approach this problem is that, I think I've mentioned it before, doing 3D rotation with 2D convolution it's really, really challenging, because again, you're trying to represent a 3D rotation with a 2D kernel. And that's actually a very hard task. So with these 2 kind of insights in mind, we basically go back and really think about how can we design a network architecture that is appropriate for the rendering task with these 2 insights in mind. So that's when we came up with RenderNet, which basically takes in a scene description, right? Like it takes in some geometry, a camera pose, and a light position, and returns a render images out. And we design the architecture to reflect the steps that involve in rendering. The first one is that we have the 3D convolutions that can deal with all of the 3D geometry. And then we have the projection step, which is basically compute the feasibility. And finally, the 2D convolution that basically computes the shading. And remember what I talk about when I say doing 3D rotation is really hard to learn. The good news is we as humans know how to represent 3D rotation really well. It's basically a 4x4 matrix, and it can be implemented very easily in any framework that you choose to use. So we make a decision that instead of letting the network learn to do rotation, we just implement it directly to the network so that the network can use all the resources to learn the actual rendering step. So that's one very important step. We explicitly implement the 3D rotation step. And then we run it through a series of 3D convolution. The projection unit is basically just an MOP that do feature selection and decide which features can be observed from this particular camera pose. And then a series of 2D convolution to get the final images. And to train this network, which is used in an image space pixel loss, either L1 or L2, and we trained it fully supervised. So it's a very simple network and fairly fast to train. And to train this network, we basically use ShapeNet chairs, which at the time, or I think it still is, one of the biggest 3D shape data set we can have. And it has like about 6,000 to 7,000 chairs, which is actually not a lot when it comes to deep learning. And we then rendered, for each share, we render 120 views out of it at different camera angles, and then train it, and then give it to RenderNet to train. So as you can see, so this is the input of the network. We get some chairs at 64 cube resolution, very sparse. And then we train it with like different types of rendering effects. So here we have foam shading, we have line drawings, we have tune shadings, we have ambient occlusion. And ambient occlusion is actually a global illumination effect. And in the traditional computer graphics pipeline, this actually takes some time to render because you need to simulate a lot of rays. Here, once the network is trained, it's just a matter of using a feed-forward network, and you can get multiple images in a matter of milliseconds. But the most exciting thing is that although we train RenderNet on chairs, because that is the biggest data set we can get our hands on, during test time, we give it shapes that completely out of distribution. So we give it a Stanford bunny, which is a very curved and organic kind of shape. And the same network that was trained on chairs can still render this really well. We push it a bit further and we say, okay, can we corrupt the input? Can we start to add lots of noise to the voxel grid? We try to downsample the voxel grid, and you can see how coarse this Stanford bunny now is with lots of like jagged outline. But because RenderNet was trained on higher quality meshes, it actually, in addition to learning to render, it's also learned to do super resolution and just like fill in all of this noise or all of this error within the input. And that's actually quite an exciting thing, because if any of you have done 3D modelings before, meshes are very particular in terms of quality. If your normal is flipped, if your triangle is having any holes, that will show in the final render. But here, actually RenderNet, in addition to doing rendering, is also doing like error correction. And finally, although we train the network on a single chair only during training, but during test time, if we give the network a sense of multiple objects with lots of occlusion going on, the model can still produce the image of that scene out. So this really shows that the network actually learns to reason over occlusion and all the lighting effects instead of just memorizing the data set. And I think that is super powerful. So yeah, so again, we train the network on chairs, but during test time, we can give it any shapes or multiple objects, and the network can still render the images out. It can also render texture. So here we basically give the network some face geometry and some encoded texture that we then map into a 3D representation and concatenate it with the geometry and then give it to RenderNet. So here again, we have quite low resolution face geometry. And this is what the network is produced with, like all details of eyes and eyebrow and things like that. And this is the ground truth images, and you can see that's pretty close. But again, the cool thing is we can also do other things than just render texture, right? What you can do is that we can now swap texture with the geometry. And for example, here we have the same geometry and we just apply a different texture on top of it. So here it's basically doing some sort of texture mapping, which in the traditional sense of computer graphics, it will require an artist to redo all of the texture on the UV wrapping. Or you can also apply exactly the same texture on different geometries, and the network will learn to map this texture to the corresponding eyes and nose position. And finally, you can also do lighting on these faces. And all of this is trained with from scratch with a network. And compare with baseline method. So this is where the decision where we say that, okay, instead of making the network learn the rotation by itself, we're doing the rotation explicitly. That's where the benefit of this really shine. So this is a work by Pusovitsky and all, where the input is also some encoded geometry, some encoded views, and some transforming parameters. So here they basically do the rotation in this compressed latent space, and this is the result. So here you can see that when it comes to rotation, doing rotation explicitly like RenderNet gives you a much crispier result. Right here is what they have. It's very blurry because you basically just interpolating rotation in this space rather than doing explicitly. But more importantly, this network again is also trained on ShapeNet chairs like RenderNet. But during test time, when it comes to generalization, if we give this network some other types of geometry, like the scene or the teddy bear or even the table, which look quite closely to a chair, this network just fails to render anything sensible out. Because basically, this network learns to memorize some sort of chair shape instead of actually learning to render. So this really shows that just by decoupling the rotation from the representation and thinking more about what's actually involved in the rendering network, we can achieve this level of generalization that cannot be done otherwise. And once the network is trained, we can just use it as a normal differentiable renderer, and then we can just do some optimization in image space to recover the input shape, the pose, the light, and some texture. So for example, given this ground truth images, that we ask RenderNet to recover the input so that it can reproduce an image as closely to the ground truth as possible. And this is a reconstruction. And once it recovered the input, it's become trivial to do things like novel view synthesis or relighting or even retexturing the face. So yeah, this is just show that RenderNet, once it's trained, it can be used to recover the input as well as any other differentiable renderers. And again, one thing that I want to highlight here is that RenderNet deals with 3D explicitly. It deals with rotation explicitly and 3D geometry. And if you compare that with another paper where they do the same task, but instead of recover explicit geometry, they basically learn a disentangle latent Z, where they say, okay, the first 10 dimension represent pose and the next 10 dimension represent light. So if you want to change the pose, you basically manipulate this latent variable. And if you compare that to RenderNet, this is our competitive method. As you rotate the face by interpolating this latent pose vector, have a lot more artifacts compared to explicitly dealing with 3D geometry. Like the result is just much sharper and producing less artifacts. The same thing with chairs. And actually with RenderNet, we can, because we recover the 3D geometry explicitly, we can recover lots of other things like elevations or lighting, while the competitive methods could not. So RenderNet is actually a very, very simple network that basically takes in the shape and the pose, camera poses, some lighting, and produce and learn to render the 2D images out. But I hope I've shown you that by learning to render, the network offers differentiability out of the box, It's very flexible. It depends on the data you train on, and it can be quite fast. When you think about replacing this with ray tracing, it can be really fast compared to hours of using rendering on computers. And another lesson that we took away from this is that by thinking a bit more about what's actually involved in the rendering process, and then use that knowledge to inform the design of the network architecture, we can have much higher image quality and especially generalization across shapes categories. So that's super cool. So from this project, we kind of asked ourselves, okay, so RenderNet is great, but we have to train it supervised. We need the corresponding pose and the corresponding shape. And if any of you have worked in 3D vision, 3D shape is actually a very hard and rare data to be able to find. So we asked ourselves if we can actually learn the 3D representation itself. Can we learn this from just images without using any 3D shapes? And basically make RenderNet less dependent on the 3D input. And that was the motivation for us to work on Polygon, which is now a generative model that learns first the representations of images. So let's come back to the motivation. Again, GAN, really nice images, very high quality, but it's very hard to have any control over what is going to be generated in the images. If you want to do that, then there's a lot of work in conditional GANs that lets you do this, but you need a corresponding labels and images to train this network. And to be honest, when I was working on this project, I couldn't ask my supervisor to give me the money to buy this data set. This is a multiplied data set. So yeah, so that's a motivation. Like I just don't have money to buy this data set to train any conditional GAN on. So can we do this unsupervised, basically? And while I was working in Polygon, there have been a lot of interest in disentangled representation learning. So here, the main idea is that they, by adding certain types of loss, either mutual information loss or the, in the case of beta B is some regularizer, they can force the network to learn a factorial representation where each factor controls one aspect of the images. The problem is for this works, they only work on synthetic data or at most phase images. So it was an interest of mine to see if we can push this further. And that's from Polygon, which is basically now can learn to disentangle pose, appearance, and shape, so that when you sample an image, you can now control the pose of the images and the identity of the object in the scene. And it works across different types of data sets with exactly the same network architecture without having to tune any losses or regularizers. So let's have a look of, so the insights that we have for Polygon. Okay, so let's start with conditional GAN. So here we have the generator and the discriminator. And the generator taking some noise vector Z and some control input, like in this case, a pose, generate an image, and then give it to the discriminator. And then the discriminator judge whether this is a fake or real images corresponding to the particular pose beta. While for Polygon, the generator also takes in some noisy and some pose beta. But as far as the discriminator goes, it's only seen real or fake images. So this is when this method becomes unsupervised, because during training, we only need basically a bunch of images of objects without any pose. We don't use any multi-view geometry, basically just a collection of images from the internet. And we did this by actually using the same insights that we have from RenderNet. So we basically asked ourselves, you know, like for the generator to produce an image, we can frame it as a rendering process. We can assume that the images that the generator produced is actually just some rendered of some 3D representation. And as we've seen from RenderNet, when it comes to rendering, there are two steps: computer visibility and computer shading. And another insight, again, is that doing 3D rotation with 2D CNN is really hard. So with that, we basically frame GAN now, the generator of GAN now as a rendering, as a render of some 3D representation. So you can see it's from the architecture as well. So here, instead of, so we started with learning a 3D representation from noisy. Instead of mapping some Z directly to some 2D feature maps, right? We actually say, no, actually, you have to first map this Z to some 3D representation, to some 3D feature maps, which has some height, some width, some depth, and all the channels. And then you can render them from a particular pose by doing 3D transformation. And then you can render them to get the final images. So this part here, it basically rendered it, right? It's 3D convolution, the projection unit, and the 2D convolution to do the shading to get the images out. But now, instead of giving a pair of pose and shapes to to this part, we actually learn the 3D transformation itself. And to train this network, we basically just use a GAN loss, which is basically, again, whether the images look real or not. And it's very important that during training, this 3D transformation step is implemented explicitly. Again, we don't want the network to have to learn to do 3D rotation from scratch. We know how to do it explicitly. So why not just do just implement it and give it to the network? And during training, because we don't know what the pose is for a particular image, we basically, during training, we just sample the pose from a uniform distribution. So we assume that the pose within the data set, the pose distribution is uniform. So we just randomly sample from that and just randomly rotate this 3D representation and then render it out. So we train it again end to end with this GAN loss, and that's basically Polygon. And what we're very interested in finding out is that how far we can use this framework. What kind of data? We're starting with very simple data sets, like the basal data sets, such as faces, and then we move on to chairs, which has a lot more variety in the geometry, but it's still synthetic. So the material and the lighting is very simple. We then move on to faces, real faces, which now start to have an extra dimension of texture and lighting, but it's still fairly simple because faces are very well parameterized. You always have 2 eyes and 1 nose and 1 mouth, but it's also a good test bed. We then push it further to the real car data set. Now it starts to get interesting because cars have, the material has specularity and reflection, and you have shadows. And for this data set, you also have an uneven distribution of pose within the car data set, right? And finally, we tested on the Elson bedroom data set, which is a very challenging data set to work on because it contains about 3 million images of bedrooms, and you have all sorts of different lighting effects, you have random writing, you have different poses and different configuration of the bedrooms. So this is like the gold standard for us to test our method on. So we train Hologan on all this data set with the same architecture, basically, without much tuning on the loss. And as you can see, now instead of in addition to sample different faces, we can actually control in which particular pose the face will be looking at. So here, basically, for each row or each column, we basically sample different Z, but keep the pose exactly the same. So here, as you can see that the pose is moving from left to right. It's literally us sample different Z and then keeping the elevation the same and just varying the azimuth of the face from 180 to 240 degrees. So it's a very intuitive way of manipulating pose. Same thing with chairs. Again, the network never seen any pose information before. All it's seen is just a bunch of images of chairs. But because it now learns a 3D representation, a full 3D representation, we can freely rotate the corresponding images out. So this is synthetic images. The next thing is faces. Cats, everyone loves cats, and you kind of have to test them on cats if you're doing machine learning nowadays. So here, cats is actually a very small data set, and it's about 6,000 images, I think. and they still managed to decompose the face geometry from the pose, and same with human faces. And finally, and it can also do the same thing with cars. So here you can see that not only does the geometry is rotated, the shadow moves correspondingly as well. And also the reflection and the specularity of the cars also changes as the pose, the camera pose changes. And it learns all of this, again, from just a collection of images of cars without any multi-view or any pose information. It also managed to separating shapes from appearance. So what we did is that instead of, we sampled 2 different Z, and then give 1 Z to the 3D convolution, to the 3D part, and 1 Z to the 2D part. Originally, this study was done in order to understand which aspect of the images is controlled by the 3D part and which aspect is controlled by the 2D part. But as you can see here, so here is a collection of face generated by Z1, right? And this is a collection of face generated by Z2. But now if we mix Z1 for the 3D part and Z2 for the 2D part, this is what we have. We have exactly the same shape and the same geometry of the face from the red row, but with the colors from the columns. So here, for example, exactly the same cars, but just now everything is red, everything is brown, everything is silver. So this also shows that the network, in addition to separating pose from identity, the network now also knows that it should separate the appearance from the shapes. And this hasn't been done before. And to be honest, if we have to find the labels to do this, it will be quite hard to find the appearance label from the shape label for this kind of data set. And this is some more sample. And this ability to separate shape and appearance persists throughout different data sets. So every data set that we work on, it now can separate pose from shape from appearance just by looking at a collection of images. And this is actually very, for us, is very surprising and also very exciting to find out, because yeah, as far as at least from our point of view, like Polygon is actually very simple. The loss is only the GAN loss. The network is made up from kind of off-the-shelf any deep learning framework that you have, but it's now without any fancy motion information loss or regularizer, we can separate this. We can separate these 3 factors out consistently throughout different data sets. And so at this point, you might ask yourself, okay, so Polygon does all of this by learning a 3D representation and then randomly transform it and then render it. How does this learned representation compare to explicit geometry as we know it? How does this compare to meshes or voxel grids as we are used to? So we compared it with Von Visual Object Network. So here they have the same insight with us. They also say that the generator, in order to generate an image, is basically a rendering process. So first, instead of they map some shape code into a 3D binary voxel grid, and then they render it using a differentiable renderer into a depth map and a silhouette map, and then using CycleGAN to transform this depth map into colored images. So here again, they also have some free they also learn or generate some free representation and then render it into 2D. And this is a comparison. So although Von uses explicit voxel geometry and they need the voxel geometry during training, you can see that as I take the 3D voxel grid and just rotate it 360 degrees, you have some artifacts at certain angles, like this one, and you also can see that at certain poses, the identity of the cars also changes. And if you compare that with Polygon, we have much less artifacts, and it can also handle much more cluttered background instead of just a white background. And if you compare this Von, which used a fairly high resolution binary voxel grid to generate these images, compared to a learned representation only from 2D images with also a much lower spatial resolution, you can start to see like the potential of a learned representation compared to any kind of explicit geometry that we used to. And this becomes very important as we want to move on to using any learn approach to 3D vision, because we really don't have enough data, 3D data, to do any kind of learning at certain scale on. And also it's become non-trivial to do 3D learning on say meshes and things like that. So having this kind of like hybrid representation that maintains certain ability to rotate and manipulate the 3D representation, but at the same time having the expressiveness of the colors and the background, that would be super useful. And this is shown by the results on the Elson bedroom data set, right? Like we just don't have enough data for the geometry of indoor scenes. So if we want to do any learning on explicit geometry, it's just really hard to do because we don't have enough data. And it's also the memory, like this 3D files become big really fast. I mean, a 3D files can go up to a few hundred megs or even 1 gig sometimes. And to load all of that into doing learning, to render an image out becomes very, very expensive. And if we want to do learning on top, it just becomes slow really quickly. While here, we can represent the whole bedroom scenes with a voxel grid of only 16 cube spatial resolution. So it's super, super coarse. But because we have multiple channels, it can encode much more information to the representation, right? So it's become a very expressive 3D representation that's learned directly from 2D images. So that was Polygon. So we show that just network into a rendering process where we say the network learned by itself to disentangle pose appearance and shapes without seeing any of these labels before. And it also helps with the training because we don't have to tune any of the loss or things like that. We just use a very simple get loss. So just by adding these 3D components, we can do so much more with the normal generator and GAN framework. So that's great. That's Hologan, and this brings us to our latest work, which is BlockGAN. So one thing that we noticed when we work with Polygon is that it learns a representation, a 3D representation, right? But if you look at this more closely, you can say that you can realize that the foreground object and the background objects basically entangle. So this 3D representation is a monolithic representation. So you can't manipulate each object in the scene separately. It always comes together. It also, and this also happens in order scene representation, like the SRN by Vincent. So at the time, all of the representation work were very motivated to learn manipulate individual objects in the scene in addition to the whole scene. So this is BlockGAN. So compared to Hologan, we only have one monolithic representation of the scene. And when we move to BlockGAN, we make an extra assumption that this 3D scene, this 3D representation that you see is actually made up of multiple objects that have their own appearance and have their own pose. So each of this yellow box is one object, and then we compose them into a scene and then render them out. So this assumption, it's a very strong one. So we're saying that the scene is not a one thing anymore. It's composed of multiple things, can be reused, and then can be combined in different ways to get the scene. And this, again, we kind of encode this knowledge or this assumption in the network architecture itself. So we assume that every image is made up of at least two objects. The first one is the background objects here, which have their own appearance and their own pose. And the rest, the remaining objects are all foreground objects, and they have their own appearance and the pose as well. But when we combine them together into one scene using the scene composer, their appearance starts to interact. So you're talking about shadows, the foreground objects casting shadows on the background. You're talking about specularity. As you move the object around, the shiny part on the materials also move along with the camera. So all of that appearance interaction between objects happens when you combine them. And then once you combine the scene, you just render them out, like Polygon, like RenderNet. And this is actually also very similar to how people do 3D modeling again. So if you have this massive complex scene, you always start with modeling each characters independently, and then you rig them and you put them together. This is kind of the same idea. And here we make some assumption for this work. So we make two assumptions. First, B, we know the category of each object in the scene advance. So objects that belongs to the same category use the same weight of the generated network. And we test, and to train this network again, we only use the GAN loss, which is a real fake loss. We don't have any extra bounding box or any extra object detection. We just use the collection of images. And so we tested on multiple data sets with varying number of objects from 1 to 4. And we also finally tested on the real car data set, which has a lot of clutter background. So for this real data set, it's always challenging to do any kind of object detection because you have all the texture going on. It's really hard to crop out which pixel belongs to the objects and things like that. So that's why we really want to test our method on this. It's kind of like one of the, again, the gold standard for us for the method to work on the real clutter data set. So for a synthetic data set, because now the network learns a object-aware representation, what you can do is that you can now independently manipulate different objects in the scene without affecting the others. So for example, here you can have, you can rotate this car or this sphere while keeping the other objects the same. And you can also see how the shadows move along with the object as the object moves along the scene. So it really understands how the object is causing occlusion, how the object is casting shadows on the background, things like that. Rotation, we can also do translation again, with translation moving out of scene and in of scene, and also along the depth dimension. And the network learns that as objects move closer to the camera, it should get bigger, and it gets smaller as it moves further out. And here we keep all the pose the same, but just changing the background condition. And you can see how if the lighting condition changes corresponding to the, so basically the network learns to capture this relationship between the appearance of different objects in the scene in addition to different poses. And finally, because each object is its own entity, we can now manipulate and changing the appearance of each object without touching the other objects in the scene. So the network basically learns that the scene is composed of multiple objects and they interact with each other in terms of appearance in a meaningful manner. And finally, we test this on the real car images. So here you can see that as the car rotates, the background now stays the same. Same with translation, same with keeping the car the same, but now just changing the background. And you can see how if you look a bit more closely, you can see how the color of the background is changed, also interact with the material of the cars, and the appearance changes correspondingly. And finally, again, keeping the background the same, but just changing the identity of the car. So now, compared to Hologram, we can now control each object in the scene and move them more freely. But for us, so compare this with a 2D method where, so here they basically have the same insights, but they say that objects within the scene, their appearance should interact with the entity. So here they use an LSTM, and they say first you generate the background, and then you generate some foreground with a corresponding mask, and then they just use this mask to composite the foreground to the background to get the final images. So here they use explicit 2D layers to decompose the scene into. So as you can see, one of the obvious disadvantage of that is that you now cannot control the pose of the objects anymore. So here, for example, as you sample different background, the cars also changes. So there's some entangled in there between the foreground object and the background object. If you keep the background the same and just sample different cars, you can see that the pose of the foreground objects also changes because you cannot control the pose explicitly anymore. And finally, this is a cool thing. So for block GAN, we took a block GAN that was trained on only a single foreground object, so only one car during test time. During train time. And during test time, we keep adding more cars in. And this is the result. Like block GAN, although for this particular block GAN model, it's never seen an image with two cars before during training, but during test time, because it's really learns a good representation of the object, we can now compose a new scene of multiple cars that is never seen before. While for the 2D method, although it uses an LSTM, and in theory, you can just keep unrolling the foreground objects, the method, this shows that the network basically just learns to memorize the data set without the ability to generalize to multiple objects. And once you have the 3D this object representation, you can also start by doing things like splitting the 3D voxel grid. So now, here I basically took two cars and just split them and then combine them, basically doing some very basic 3D modeling operation, right? Or I can also take them and just stretch them in different ways. So none of this transformation was observed during training. And this really shows that the object representation learned by block GAN, it's independent, it's meaningful, and it can be manipulated very intuitively just by applying 3D transformation on it. But again, the thing that excites me the most is that although these networks, for example, for these 3 rows was trained on a single foreground object, in test time, you can add a lot more foreground objects. So here I add like 4 extra cars. And for every cars that I add, it also learns that it should cast some shadows, it should block the other cars and things like that, although during training time, it's never seen 2 cars before. And it works consistently throughout the synthetic data set and the real car data set. So this ability to generalize beyond the data set really is kind of like, again, an argument for using these inductive biases in your network. So it's not only help you learn the disentangled representation, it's also help you generalize way beyond the training data set that the network was trained on. So for block GAN, as I just shown you, is an extension of Polygon where now the network learned a composable scene representation, so that now you can create new scenes by just adding or removing objects instead of just manipulating the pose and appearance anymore. And this is where it's kind of like an advantage of using the voxel representation compared to, say, the implicit representation, because with this voxel representation, spatial manipulation and like combining different objects become very intuitive. While if you think about using MLPs to represent a scene, it's actually not trivial to think about how we can even start segmented this representation into objects. It's actually not so clear. So throughout these 3 works, I hope that I'm showing you that by just thinking a bit more about what kind of knowledge and what kind of inductive biases that we know about the 3D world, just think about a bit more and then inject that into a network architecture design, you can achieve a lot of generalization and disentanglement without even having to fiddle with the loss functions or the regularizers or using any fancy components with the convolution layers. And we started with, like just thinking about how can we design a network architecture to learn rendering more efficiently? And then we start to think about how can we use that to learn a more expressive representation of the 3D world? And finally, how we can even expand it further and now learn a composable representation of the world so that we can now manipulate different objects and generalizing the number of objects way beyond the training set. So where do we go from here? So I'm gonna start playing a short clip, and then we'll take it from there. Okay, I wish there was a sound effect. It's a lot funnier when there's a sound. But so I choose. So this is a very so this is a very simple scene, right? It's basically synthetic. You have a white background with some letters. But as humans, when we look at this scene, we immediately know that this is composed of 6 objects in 3D, because we know that this lamp is blocking the letters, right? So as humans, we just look at this for a few seconds, we know immediately how the scene is composed. And we also know the lighting, the material property of this scene, right? We know that the light is shining some light on the letters, and you have reflections, and you have shadows and things like that. And finally, we know that in this scene, there's a lot of the physics of the world's going on. You have gravity, you have different properties of materials and things like that. So even in this very simple scene, there's a lot going on, and there's a lot that help us. And I think moving forward, there's a lot of these inductive biases that we can think about in order to inform our machine learning methods a lot more. I think the computer graphics community are very good at this. Like the whole thing about rendering is to think about what kind of physical properties of materials and lighting that they can learn and simulate in the rendering pipeline in order to get photoreal images, right? It takes a lot of time and it's very tedious, but they are very good at thinking about what kind of physical-based rendering they should design. The machine learning community are very good at like learning from data and pushing the quality of this. But I feel like there's an opportunity of combining the knowledge of the physical world that the computer graphics folks are really good at with the data-driven approach. And it's not just because it gives us better results, but I think it gives us a better representation of the world, and it helps a lot with generalization. And I think this will be hugely beneficial for lots of applications. You're talking about games and movies and VR and AR, but also in terms of like robot learning and self-driving cars. So using inductive biases of data-driven approach give us an interpretability, generalization, and hopefully more data efficiencies when it comes to learning methods. And before I finish, I would like to thank my collaborators. These are amazing people to work with, and I learn a lot from them. And with that, I would like to end my talk.